For most of the 20th century, the story we told about the universe had a clean, comforting structure. There was nothing. Then, at a single instant, a singularity of infinite density and temperature, 13.8 billion years ago, there was everything. Space itself began. Time itself began. The Big Bang wasn't an explosion happening within space. It was the origin of space, the starting gun for existence itself. This is the story most of us learned in school. It's the story that appears in popular science books, in documentaries, in the confident narration of countless YouTube videos. The Big Bang was the beginning, full stop. Before it, the question, what happened before, was treated as meaningless, like asking, what's north of the North Pole? But here's what's changed, and changed significantly, in the physics community over the past 2 decades. A growing number of serious theoretical physicists no longer think the Big Bang was the actual beginning of everything. Not because they found some mystical alternative, but because the mathematics describing the early universe, when pushed to its logical extreme, runs into problems that suggest something existed before, or that before might not even be the right way to think about it, because the structure of time itself near the Big Bang may be far stranger than the simple picture suggests. I want to walk through why physicists started questioning this, what the leading alternative models actually propose, and why this isn't a fringe debate but a genuinely active area of mainstream theoretical cosmology. To understand why the Big Bang singularity became a problem rather than an answer, you need to understand what a singularity actually represents in physics, and it's not what most people assume. When physicists say the universe began at a singularity, they don't mean we have a complete theory that describes a point of infinite density giving rise to everything. They mean something closer to the opposite. When you take Einstein's equations of general relativity and run them backward in time, following the universe's expansion in reverse, the density and temperature increase without limit, and the equations themselves break down, producing meaningless results like infinity. A singularity, in this context, isn't a description of what actually happened. It's a signal that our theory has stopped being applicable. This happened before, in the history of physics, and the precedent is instructive. In the early 20th century, when physicists first applied general relativity to extremely dense objects, they found that the equations predicted infinite density at the center of certain collapsed stars, what we now call black holes. For decades, many physicists, including Einstein himself, treated this as evidence that something was wrong with the theory, or that such extreme collapse simply couldn't happen in reality. It took decades of additional theoretical and observational work to establish that black holes are real, while the question of what actually happens at their center, whether the singularity is a genuine physical reality, or again, a sign that general relativity needs to be replaced by a more complete quantum theory at extreme densities, remains unresolved to this day. The Big Bang singularity faces the exact same issue. When physicists run the equations of general relativity backward toward the beginning of the universe, they reach a point, roughly 10 to the negative 43 seconds after what we call time zero, a moment known as the Planck time, where the predicted density and curvature of spacetime becomes so extreme that general relativity, by its own internal logic, stops being a reliable description of reality. At these scales, quantum effects on the structure of spacetime itself should become significant, and we don't yet have a complete, experimentally verified theory of quantum gravity that tells us what actually happens under these conditions. In other words, the Big Bang singularity isn't a confirmed scientific fact about the literal beginning of everything. It's the point where our best current theory admits it doesn't know what's happening and hands the problem off to a more complete theory we don't yet fully possess. This gap, the unknown physics of the very earliest moments of the universe, is exactly where alternative models of cosmic origin have flourished. I want to walk through several of the most seriously considered alternatives, because each one represents a genuinely different answer to the question of what, if anything, came before what we call the Big Bang. The first major alternative comes from a branch of theoretical physics called loop quantum cosmology, an application of loop quantum gravity, one of the leading candidate theories for unifying quantum mechanics with general relativity, to the conditions of the early universe. In standard general relativity, as matter is compressed to higher and higher densities, gravity becomes stronger and stronger without limit, eventually producing the singularity. Loop quantum gravity proposes that space-time itself has a discrete, granular structure at the smallest scales. That space isn't infinitely divisible, but is instead built from tiny, indivisible units, somewhat analogous to how matter is built from atoms, rather than being infinitely divisible. When this granular structure of space-time is incorporated into cosmological models, something remarkable happens to the mathematics describing the early universe. As density approaches the extreme values associated with the classical singularity, a powerful quantum gravitational repulsion emerges, preventing density from ever actually reaching infinity. Instead of collapsing to a singular point, the model predicts a bounce. The universe reaches a maximum density, then rebounds into expansion. Under this picture, the Big Bang wasn't the beginning of everything. It was the moment a previous, contracting universe reached its maximum compression and bounced back into expansion, becoming what we observe as our universe today. This is sometimes called the Big Bounce model, and it has a striking philosophical implication. If it's correct, our universe may be just one phase in an ongoing, possibly eternal cycle of cosmic contraction and expansion, with the Big Bang representing not creation from nothing, but a transition point between one cosmic era and the next. The second major alternative comes from string theory and proposes something even stranger, that our universe's beginning resulted from a collision between higher dimensional structures called branes. In certain versions of string theory, our observable universe, the three dimensions of space we move through, plus time, is understood as a kind of membrane, or brane, embedded within a higher dimensional space. Some models propose that there could be multiple such branes existing in this higher dimensional space, occasionally drifting close to one another. The ekpyrotic model, developed in the early 2000s by physicists including Paul Steinhardt and Neil Turok, proposes that the Big Bang was the result of a collision between two such branes. When these higher dimensional membranes collided, the enormous energy released in the collision is what we observe as the hot, dense early state of our universe, the conditions traditionally attributed to the Big Bang singularity. Under this model, before our universe's beginning, there existed two separate branes, drifting through higher dimensional space, slowly approaching each other over an enormous span of time, before colliding and producing the burst of energy that initiated our universe's expansion. Some versions of this model propose that this process could be cyclic, that after our universe eventually reaches a state of maximum expansion and dilution far in the future, the branes could separate, then approach again, triggering another collision and another Big Bang, in a process that repeats indefinitely across what would effectively be an eternal, cyclic multiverse. This model, like the loop quantum cosmology bounce, replaces the singular beginning with a transitional event, not creation from nothing, but a transformation from one cosmic state to another, governed by physics, operating in dimensions beyond our ordinary three-dimensional experience. The third major alternative is, in some ways, the most radical, because it doesn't just question what happened before the Big Bang, it questions the very assumption that before is even a meaningful concept in this context. This is the framework called eternal inflation, developed from the standard inflationary theory that already forms part of mainstream Big Bang cosmology. Inflationary theory, first proposed in the early 1980s, suggests that in the first tiny fraction of a second after the traditional Big Bang, the universe underwent an extraordinarily rapid period of exponential expansion, growing by an enormous factor in an almost unimaginably brief interval. This isn't speculative fringe physics. Inflationary theory is well supported by detailed observations of the cosmic microwave background and is considered a standard, if still actively researched, component of modern cosmology. But when physicists examined the mathematics of inflation carefully, they found something unexpected. Under quite general conditions, the process of inflation, once started, doesn't necessarily stop everywhere at once. While inflation ended in our particular region of space, giving rise to the universe we observe, quantum fluctuations mean that inflation may continue indefinitely in other regions, constantly spawning new bubble universes, each one undergoing its own version of a Big Bang, as inflation ends locally within that bubble, while inflation continues eternally in the surrounding space between bubbles. Under this model, called eternal inflation, our Big Bang wasn't a unique, singular event marking the beginning of all existence. It was simply the moment inflation ended within our particular bubble of space, one event among a potentially infinite number of similar events happening throughout an eternally inflating, ever-expanding background, a background that has no beginning and no end, that has always existed and will always continue to exist, spawning new universes continuously, of which ours is just one undistinguished example. This model directly implies the existence of a multiverse, not as a philosophical speculation, but as a fairly natural mathematical consequence of taking standard inflationary theory seriously and following its implications to their logical conclusion. I want to be honest about where these ideas currently stand within the scientific community, because there's an important distinction between seriously considered theoretical framework and experimentally confirmed scientific fact. None of these alternatives to a singular cosmic beginning have been confirmed observationally. The Big Bounce, the ekpyrotic brane collision model, and eternal inflation all remain theoretical proposals, motivated by genuine problems with the standard singular Big Bang picture, but lacking the kind of direct observational confirmation that would elevate them from serious hypothesis to established science. This is partly because testing these models is extraordinarily difficult. The events they describe, whatever happened before the moment we call the Big Bang, occurred by definition before the universe became transparent to light, roughly 380,000 years after the traditional Big Bang. Everything before that point is, in a sense, hidden behind a curtain that electromagnetic observation cannot penetrate directly. Researchers are searching for indirect signatures, specific patterns in the cosmic microwave background, particular statistical properties of the large-scale distribution of galaxies, or potentially future detections of primordial gravitational waves that different models predict differently, and that might eventually allow us to distinguish between these competing theoretical frameworks. The honest scientific position, as of now, is this. We know the universe, as we currently understand it, had an early hot, dense phase, roughly 13.8 billion years ago, that subsequently cooled and expanded into the cosmos we observe today. This is extremely well confirmed by multiple independent lines of evidence. What we don't know, with the same level of confidence, is whether this hot, dense phase represents the absolute beginning of all existence, or whether it was instead a transition, a bounce, a brane collision, the local end of an eternally inflating background, from some prior state that our current observations cannot directly access. There's something genuinely profound in sitting with this uncertainty, rather than rushing past it for a comfortable, simple answer. For most of human history, every culture that has asked where did everything come from has arrived at some version of a creation story, a moment when nothing became something, when the world as we know it began. Modern physics, in developing the Big Bang model, seemed at first to provide a scientific version of exactly this kind of story, a clean, singular beginning, dramatic and definite. But the deeper physics has dug into the problem, the less certain that clean picture has become. Not because the evidence for an early hot, dense universe has weakened, it hasn't, it remains as strong as ever, but because the question of what that early state actually represents, philosophically and physically, has become genuinely more complicated, not less. Maybe the universe did begin from absolute nothing, 13.8 billion years ago, in a way that current physics simply hasn't found the right mathematical framework to describe yet. Maybe it bounced from a previous contracting phase, part of an eternal cycle stretching infinitely into the past. Maybe it emerged from a brane collision in a higher dimensional space we cannot directly perceive. Maybe it's one bubble among an infinite, eternally inflating multiverse, with no true beginning at all. We genuinely don't know. And I think that's a more honest and ultimately more interesting place to leave this question than any confident, simple answer would be. The universe we live in had a beginning, in the sense that there was a moment 13.8 billion years ago when everything we observe started its current expansion from an extraordinarily hot, dense state. Whether that moment was the beginning of everything that has ever existed, or simply the most recent chapter in a story, stretching back much further than we can currently see, that remains one of the genuinely open questions at the absolute frontier of physics. We are still trying to find out.